Okay, first of all, you can interact with me during the session. You've already shown me that you can find the smiley face button. There's also a frowny face, and you can put your hand up as well. So if you really want to grab my attention, if you press the hand, the sort of ghostly blue hand with the green arrow next to it, then that will actually ring a bell in my ear, and it will tell me that you want my attention for some reason, so you can do that. The main way that you'll probably communicate with me and others is by using the chat area. Now, Stephen's already been using that. If you type a message in the long, thin, white rectangle, hit return, you can send messages to everyone in the room. So what I'll do is I'll keep an eye on that. I think Stephen will also be keeping an eye on it. He might be able to answer some of your questions. But if you particularly want to ask me something, I'll keep an eye on that. And if I can answer your question, I'll try to do that in the audio. There are also drawing tools. I'm not sure whether we'll be using those, but you should all have those switched on. It's a bit like Microsoft Paint. You can sort of scribble on the screen. You can draw basic shapes. Can't think that we'll be using that, but they're there nonetheless. And finally, we'd like to sort of get an idea of where you all are, and this is our first moment of interaction. What you should do to show me this is if you click on the sort of sparkly wand icon, which is in the 5th row down of the drawing tools, that should switch on a pointer, and I'm hoping that if you do that, you'll be able to position a dot where you are in the country. Lots of people in the Midlands. I'm trying to place my dot there. I'm in the town of Warwick at the moment. My base for my job is at the University of Warwick, and I can see quite a few of you from the Midlands. But we've got a nice spread there of people. Okay, so without any further ado, let's get cracking with the talk for this evening. What I'd like to talk to you about is mathematics in 3 different areas. Probably the majority of the time in my talk will be spent talking about search engines. There's and using the example of Google to illustrate some fairly simple mathematical ideas being used in a very powerful way. One of my great hobbies is video games, and I find that using video games as a vehicle to promote mathematics to young people is a really powerful thing to do, especially when you can show them some of the topics that they tend not to like so much at certain ages, like vectors, has such a key role in computer graphics. And then finally, I'd like to touch on, very briefly, on social networks. There's one particularly neat application of vectors that I'd like to show you in that area. So those are the things I'd like to cover this evening. And as I say, the motivation for this material, the reason I put all this together, was to try to promote mathematics to young people. And the first thing I asked myself when I thought about how that could be done was, well, how do we answer these sort of classic questions that arise in the maths classroom, such as, at GCSE level, why do we study simultaneous equations? I think that, as somebody who's involved in teaching young people, there are certain questions that you don't necessarily look forward to too much because they're not that easy to answer. So to give a convincing, short, mathematically credible answer to why do we study simultaneous equations is not a trivial thing to do. So I'm hoping that in 45 minutes time you'll all see that there is a really nice straightforward answer you can give to that. Similarly, why do we study angles and triangles? Students, they look at triangles from a young age. They learn about types of triangles. They learn about Pythagoras' theorem and trigonometry. They're doing a lot of work with angles and triangles. So how can we give a really convincing answer to a young person as to why they should be interested in learning those skills? I'll say something about algebra in this talk. What can we do with algebra? What's the point of algebra? And obviously this is a really deep question, but it's something that as people who might be engaged with trying to convince young people that mathematics is a good thing, we should have an answer to this question. So I'll try to sort of touch on that. And then finally, as you'll see in a moment, most of what I'm going to be doing this evening involves vectors in some way. And my experience of talking to young people about vectors, especially when they're sort of 14 or 15, they may have just met vectors, is that they really cannot see what that mathematical idea is giving them. I'm sure this is partly because when you first meet vectors, you really can't do very much with them. Until you've done a certain amount of material on vectors, it's very difficult to see how they can be powerful in any way. So that's going to be the, if one of these questions is the big theme of this evening, it will be, what can we do with vectors? Okay, so that's my aim then, I guess, for the next 45 minutes, is to sort of send you all away with a new outlook on all of these questions and topics. Okay, so we're going to start with search engines, and we're going to talk about the example of Google. And I'm calling this the world's most valuable simultaneous equations. These two guys invented Google. We've got Page and Brin here. They were at university in California in the 1990s, studying computer science as it happens, and they had an idea for a new search engine which they went away and built. They called the prototype version of it Backrub, and they sort of let their friends and colleagues loose on that. Their friends and colleagues said it was a really powerful search engine. It was better than the things that were around before. And a few years later, Google was launched to the world. Within about 6 months of Google being available, the whole world had decided it was much better than the search engines that were around before that. And the majority of people who were using the internet and searching the internet had chosen to use Google, largely by word-of-mouth recommendations as it happens. So what I'd like to do to begin with is to explore what it was about Google that was so much better than the search engines that were around before Google. I thought I'd just give you an opportunity to think about this. I've listed 4 possible reasons here that people may have preferred to use Google than whatever they were using before. I'm not going to open this up as a poll, but if you want to tell me which of those 4 things you think was perhaps the most significant feature of Google, you can either hit A, B, C, or D, or you can type it into the chat box there. Sorry, I should point out where you do this. Some of you have found it. It's just below the list of your names again. There's A, B, C, and D options. Okay, so actually you're fairly sort of evenly distributed across the options at the moment, although the most popular answer from those who've given me an answer is C. And the answer to this is by a long way C. The thing that people really enjoyed about Google, well, not enjoyed, but found useful about Google, was the way that it ordered search results. So you would ask it to find plumber Warwick. It would find 18,000 results for plumber Warwick, and then it would have this nice habit of selecting from those 18,000 possible web pages the one that would be most useful to you and placing that first on the page of return results, then deciding which one it thinks would be second most useful, placing that second on the page of return results. And what I'd like to explore in the next few minutes is how it actually did that. What I'd like to do first of all is to go back to some ideas that were around before Google. This idea of devising the charts, in other words, deciding the order to present found web pages to you once you've carried out a search, is called page ranking. And before I get into how Google did that differently to other search engines, I'd just like to say a little bit about how search engines before Google did that. So what we've got here is a very simplified model of the internet. Well, it's not really a model, it's just a scaled down version. These are 3 websites only: website 1, website 2, website 3. The arrows here represent hyperlinks between the websites. So you can be on website 1, you can click your mouse, follow this hyperlink, and you'll pop up on website 2. Now, just for the next 15 minutes or so, I'd like you to imagine that this is the whole of the World Wide Web, and we're going to decide how we might classify these pages in terms of page ranking. So which one should appear first, which one should appear second, which one should appear third, if they were all found when someone searched the internet. Okay, now prior to Google, what used to happen essentially, and there are some quite big simplifications going on here, but the gist of what I'm saying is certainly true. Prior to Google, what used to happen was that search engines would count how many incoming links there were to a website. And the more incoming links you had to your website or web page, the higher up the charts you would appear. So if we take this example here, we can see, for example, that website 1 has just one incoming link, and that's the one currently shown in red across the bottom from website 3. Website 2 has 2 incoming links, one from website 1, one from website 2. And website 3 also has 2 incoming links, and you can see those there. So if these were the only 3 websites in the world and they all contain the words Plumber Warwick, so they were found upon a search for Plumber Warwick, what we would find is that these 2 were equal first, because they both have 2 incoming links, and then website 1 is behind them in what you might call second or third, depending on your point of view, but it's behind those 2. And the idea here is clearly that each incoming link is like a recommendation. So the fact that somebody who works on website 2 bothered to set up a link to website 3 means that they found it useful or interesting or relevant for something. So this is like a recommendation, and website 3 has 2 recommendations. Website 2 also got 2 recommendations, whereas website 1 only had 1 recommendation. Hence this ordering of them for search engines prior to Google. So that's what used to happen prior to Google. And the thing that happened with the 2 guys who invented Google was that and the way that they thought they could do better than that was by not counting each recommendation as, well, not saying that all recommendations are equal. So what they thought was that actually it's not just how many recommendations or links in you have, it's who are they from. We need a mathematical way to capture this idea of the recommendation as having a value depending on who it comes from in some mathematics. So that's what they set out to do. So not all recommendations are equal anymore. We're going to take into account who they come from. So they thought that a recommendation for your site from, a link to your site from bbc.co.uk should do more for your chart position than a link from, say, barometerworld.co.uk. They wanted to capture that idea in some mathematics. Okay, here's how they did it. So what they said was that each website is going to have a score. Website 1 will have a score of X, website 2 will have a score of Y, and website 3 will have a score of Z. And what you've got to do now is imagine that, for example, website 3 here is casting a vote for both of website 2 and website 1. Those are the 2 hyperlinks that it makes, one to website 1 and one to website 2. Now the total vote that it can cast is equal to its score, which we've just decided will be Z, and it has to distribute that vote evenly across the votes that it's making. So in other words, this vote down here is going to be worth Z over 2, and the other link it's making, the one from 3 to 2 up here, is worth the other half of Z. That will also be worth Z over 2. Okay, so let me just check that you've got that idea. So if we consider website 1 now, and this vote or link over to website 2, can somebody tell me what they think the value of that will be? Yep, X over 2, excellent. So yeah, everyone's saying X over 2, which is spot on, of course, and the reason for that is that website 1 has a score of X. It's linking out to both of the other 2 websites, or it's voting for both of them, so it has to distribute X evenly across those 2, so half of X each. And finally, what about this link here? How much value does this have? Yeah. So this will be worth the whole of Y. So what we've got now is each of the links has a value which is dependent on the origin of the link. Okay, and what we can do now is we can look at the votes received by each of the 3 websites. So if we create a little table down here, let's look at website 1, website 2 and website 3. So website 1 is receiving votes worth Z over 2. That's this link across the bottom from right to left. So the vote received there, Z over 2 for website 1. For website 2, it's X over 2 plus Z over 2. And that's this one here, going from 1 to 2, and this one here, going from 3 to 2. And then finally, website 3 is receiving Y plus X over 2. So X over 2 plus Y. Okay, and we can see here that we've counted all the votes because here are the two halves of Z, here are the two halves of X, and there's all of Y, so that's the total of X and Y and Z. Okay, and the clever part about what happens next is that we look at the vote received by website 1, which is Z over 2, and what we say is, well, that will be your score, so that will be equal to X. Website 2, you're receiving this expression as the vote you get, so that will be your score, that will be equal to Y. Website 3, you receive this much vote, X over 2 plus Y, so that will be your score, that will be Z. So what we see here then is a system of simultaneous equations in 3 variables, admittedly at this point, because we're imagining the World Wide Web is 3 websites. And we have to solve them simultaneously, so we have to find values of X, Y, and Z, which make all 3 work at the same time. There's a trivial solution. Can anyone spot that? Well, a bit of a clue with the word trivial there. Yeah, X equals 0, Y equals 0, Z equals 0 will work. But there are other solutions as well, and it's one of the other solutions that we're looking for. So if any of you guys are in the position of needing to convince somebody that simultaneous equations is a useful thing to be able to do, I think this is a winning argument based on, you know, a modern and relevant piece of technology, and you can get to the mathematics very quickly, so you can actually draw this diagram. It's not too hard to explain this, and you get to a point where you're looking at some simultaneous equations. So what I'd like to do next is just explore this a little bit more. This is the set of equations that we were just looking at. Of course, you can write these as a matrix equation, and that works out fairly nicely like this. And so at this point, what you realize is that what you're looking for in the values X, Y, and Z is that they are components in an eigenvector of this matrix whose eigenvalue is 1. So it gets mapped to 1 times itself. It's a fixed point of this matrix. And that's really nice. There's a lot of mathematics in this that you can read about if you want to. This matrix here is actually called a stochastic matrix. You can see that its columns add up to 1. The total of this column is 1, the total of this column is 1, the total of this column is 1. And there's a theorem in mathematics which says that if you have a stochastic matrix of any size, square matrix, then it will have its eigenvalues will all have modulus less than 1. Well, sorry, less than or equal to 1. And also there will be an eigenvalue, there will be an eigenvalue of the number 1 as well. So that means you will be able to find an eigenvector whose eigenvalue is +1, and so these solutions will exist, and you know, an eigenvector, i.e. a vector which isn't just the 0 vector, so a non-trivial solution of this system of equations is guaranteed to exist by a piece of mathematics. What I'd just like to look at next is ways that you can approximate solutions to these. Of course, because this is a fixed point of this matrix, and because all of the eigenvalues of this matrix have modulus less than or equal to 1, this eigenvector is what we call the dominant eigenvector. And what this means is if you start with any vector and feed it into this matrix to get a new vector, feed your new vector back in to get yet another new vector, and so on and so on and so on, the vector that you will get over, you know, as n increases in that sort of that sequence of vectors will tend towards a solution of this equation. It's a little bit like fixed point iteration in, you know, sort of A-level mathematics. And we can have a quick look at this now. So what we're doing here is we're starting off with this vector 1, 1, 1. Ignore the sort of box notation here. This is a vector. And imagine that we applied this matrix to it. So what would we get? Well, it turns out you would get this vector. Now imagine that you applied this matrix to this to get a further vector. That would be this one. And again, and again, and again, so as we continue to do that, so if we look at this sequence of vectors, it actually tends to a solution of these equations. And so what we can see is that for this system here, we're missing a link there in that diagram. You can see that Z has the highest value, followed by Y, followed by X. And so website 3 would appear top in it if it was found in Google, website 2 behind it, and website 1 behind that. And I'm guessing that you may have guessed that from looking at the system of hyperlinks anyway. What I'd like to show you next is another equivalent idea to this, because you can imagine this whole piece of mathematics as an exercise in Markov chains. In fact, the two guys who invented Google envisaged this notion of a random surfer, which is equivalent to something from considering this as a Markov chain. I'd just like to touch on this very, very briefly. Now, I'm hoping that I'm going to be able to share an application with you, so just give me a second for this. Okay, let's see if this is going to work. What I'm hoping is that you can now see something called random surfer simulation. Now, I know that this can take a while to come through, so if you can give me the smiley face when you can see that, that would be great. Okay, what I'd like to do now is try to explain to you. Can you see my cursor there, sort of in the middle of that system of equations just moving around? Okay, good. Okay, what I'd like you to imagine is that we take a person and we put them at random on either website 1 or website 2 or website 3 to begin with. So you can imagine, you know, you might roll a dice, and if you get 1 or 2, you put them on 1. If you get 3 or 4, you put them on 2. If you get 5 or 6, you put them on 3. So you randomly put them in a starting position. Imagine that we put them in 3. So then they would have a choice of whether to surf to website 1 or to website 2, because there are those 2 links available from website 3. And they would make that choice at random, so they'd flip a coin to decide between following that link or that link. Imagine that they went to website 1, well then they'd have another choice because they could go over to website 2 or down to website 3. If they end up on website 2, the only thing they can do is go down to website 3. And what we're going to do is we're going to let our surfer click around for about 20 clicks, and we're going to record where they finish. Okay, so let's see if this works. Okay. There's our surfer represented as a droplet, and I'm going to just speed that up. What's happening here then is, I'm not sure how well you can see this, but they were just surfing around, and I don't think we gave them 20 clicks, maybe we gave them 10 clicks, but after 10 clicks they ended up on website 1. And now what I'm going to do is just generate a whole load of these, and we're going to let them surf around. We're going to record the proportion of them that finished their journey of 10 clicks, I think it is, on each of the 3 websites. Now, this is moving really fast on my screen, and I'm imagining that because essentially what you're getting is sort of an image of this okay, on your screens. Are you able to see this okay? Can you see what's going on, essentially? Give me a smiley face or a frowny face. Maybe the audio slowed down a bit as well. Okay, I think we're getting a few slowdown problems. But what we're seeing so far is that of our who knows how many surfers, 18% of them ended their journey on, or 19% ended their journey on site 1, 32% ended on site 2, and 49% ended on site 3. And it turns out that these 3 numbers, 0.2, 0.3-ish, and 0.47, 0.48-ish, are very good approximations to X and Y and Z, as in the previous discussion. Let me close that down because I think that's not helping our performance levels here. So let's go back into the application. I did want to sort of do an exercise with you, which is for you to guess which of these 4 websites, well, what order do you think these would appear in if they were found in Google, given what you now know. I'm just going to give you 30 seconds or so to type into the chat box an order for these websites appearing if found on a search engine like Google. Yeah, so we've got 3421, we've got 3412, 3124. Okay, well, I'll risk this one more time. Incidentally, what I'm using for this is a really nice bit of software, which I do recommend, called Game Maker. If any of you are interested in fiddling about with homemade video games, then Game Maker is a great way to do that, especially if you don't really know very much programming. There are some nice tutorials to get into it, and that's how I made these little applications. Okay, so let's run this one. Oh, am I sharing it with you? I don't think I am I? Okay, this has already started running, and I'm going to speed it up. Again, assuming that you can see this, what you can see here is that sites 3 and 4 seem to have approximately the same score. Site 1 is certainly in 3rd position, and site 2 is in 4th position. Can you see that actually? I'm sort of conscious that there can be a delay with things like this, and I don't want to move on before you've kind of seen that. Yeah, so site 3 is, typically people say that site 3 will win this because it has 3 hyperlinks coming in, and it does, but actually site 4 is joint first because it has a hyperlink from site 3, and site 3 is only linking to site 4. So one of the equations, if you think about it, is actually the score for site 3 equals the score for site 4. It's a consequence of site 3 having that single hyperlink out to site 4. So although not many sites are linking to site 4, because it has a link from site 3, it does well in this. So you can see the idea there, sort of in action. Okay, right, that's the first part of my talk over, and in the remaining time I'd just like to talk to you fairly briefly about applications of vectors in gaming and graphics, and then move on to an idea in social networks. Now, okay, what I'm trying to show you here is, is this going to play ball? Right, well I can't see the video clip, so I'm assuming that you can't either. Is that true? Oh, here we go. Something's just sprung into action. So this is a PS3 game called MotorStorm. This is actually a sort of tech demo of it. This is one of the first games that came out, but this is the kind of standard in graphics and well, lots of other mathematical ideas that we're seeing in the current generation of consoles. You can see, for example, that we're in sunlight now and there are shadows. So one of the things I'd like to talk to you about is how do you deal with lighting in video games. There are lots of other things going on in this, like there's lots of texture and camera angles that are being moved around. There's the AI of the opposing vehicles and so on. So that just kind of sets the scene for a few of the things that I'd like to talk to you about. Of course, if you rip off the texture from a video game or a film, what you'll see underneath it is this thing the programmer calls the triangle mesh. I'll gather that some of you couldn't see that. Oh well. There's another video clip later on, but we'll see how we get on with that. And you can see that in this simple scene, the sort of environment is built from triangles, and you can see how different sizes and shapes of triangles represent the kind of troughs and slopes and ridges and valleys in this scene. And one of the things that the programmer has to do, of course, is to cover the triangle mesh from you. You're not supposed to see that if you're playing the game or watching the film. So this process is called adding texture, and I just wanted to mention that very briefly because it is actually an application of linear algebra and matrices. So there's the scene with the texture put in, and there's the scene as its triangle mesh. All that's really happened in terms of console and film technology over the last 20 years or so is that processors have been getting faster forever, but back in 1993 or so, the PlayStation 1 console, or the consoles around just that one came out, they could move about 360,000 polygons on screen per second, whereas the current generation of games consoles, they can do many, many more polygon updates on screen per second. And of course what this means is you can build your characters now using a lot more triangles or polygons, and you can make them much smaller. And as a consequence of that, your graphics tend to look less polygon-y or triangle-y. But I did say I just mentioned texture very briefly. All the textures for a film or a game will be stored in a sort of standard way as a square, say, in the in the computer memory, and then you need to apply mappings so that they fit into the piece of polygon that's supposed to have that look. And a lot of these kind of transformations are done using matrices. I'm kind of conscious of time, so I want to skip on to what I think is one of the most interesting parts of this, which is lighting. So you can see in this scene, it's only got a few polygons, like that would be a polygon there at the back. The floor here might be 4 or 5 polygons, there are some other polygons. Maybe there's 20 polygons in this scene. And you can see that the texture has been put in, so this brick texture has been overlaid into this quadrilateral, and the slabby texture has gone down here. Now imagine that there's a light somewhere in the scene, and we've got to work out what all these surfaces should look like with respect to that light. So somehow we need to calculate that this is how this thing should look. And of course this light might move, or the camera angle might move, and we need to look at different effects. Of course, this is a great thing to say to students who are just learning about vectors, because what we can say to them is that a vector provides us with a way of changing sort of our notion of direction or arrows or pointing into some numbers. So we can take this 2-dimensional vector and we can represent it as 2 numbers, and we can do something similar in 3 dimensions. And of course what this means is that we can now start talking to computers about direction, because a computer will only understand numbers, and so we need to have a way of translating direction into numbers, and a vector provides that. So there's a really nice sort of mathematical message there that young people, I think, will be able to take on board and understand quite easily about direction. And of course lighting is all about direction, so we're kind of in business now if we want to do lighting on a computer. What I'm about to show you is a simple application of the scalar product. So we can take our 2 vectors, we can put them tail to tail, and there's a fairly straightforward way of calculating the angle between them, using something called the scalar product. So what is this application then? So what I need you to do here is to imagine, I'll try and draw a diagram on this screen. Okay, traditionally my diagrams are absolutely appalling. So imagine that this is a piece of a polygon in the scene from a video game. What I'd like to talk to you about is this thing called the normal vector. So this vector sticks out of our surface in such a way that it makes a right angle with the surface, in every direction. So if we were to sort of drop this down onto the surface, it would fall through 90 degrees, whichever direction we pushed it through. So that vector there is called the normal vector, and that's got a key role in lighting. In this slide, this vector here is supposed to be the normal vector. And what we're imagining here is that there's light coming in from a light source, represented as this other vector going in the opposite direction down here. And of course, if the angle between our light vector and our normal vector is 0, it means that the light is hitting our surface kind of full on, and it should light up the surface as much as possible and make it as bright as possible. Whereas if the angle between the light coming in and the normal vector is larger, then this should be a slightly darker surface, and so on, getting darker and darker as the angle increases. So we can easily calculate that angle using the scalar product, and then we can set the brightness accordingly. And the next thing I'd like to show you is an actual demonstration of that. Oh, now I'm getting an autograph error. I'm hoping that you can see that. Can you see a nice red surface looking at you in 3 dimensions? Okay, excellent. Right, let me rotate this so that you can see the relationship between this and what I was just saying. The green thing there is the normal vector. And what you've got to do, you can actually move the lighting around in this program in Autograph. And at the moment it's set up. Imagine that your sort of face is the sun, yeah? So the light is going in from where you're looking in that direction, and the normal vector at the moment is pointing straight back, and you can see we get a nice bright red surface there. So what I'm going to do now is I'm going to increase the angle between the light going in, which is kind of perpendicular to the screen, and the normal vector. So you'll see the normal vector appear, and you can imagine this angle increasing. But what I'd like you to do is look at the colour of the surface. So it goes to a darker red, a much darker red, a very, very, very dark red, and black. And then bringing it back again, lightening up to a lighter red, lighter red, lighter red, lightest red. And what's going on there is that we're calculating the angle between the green vector and the light vector, and we're setting the brightness accordingly. And you can see it's a very convincing illusion of something happening in 3 dimensions. It's kind of mimicking what we would expect to see in terms of a surface being lit from our experience of that in the real world. And of course, it's fooling our brain into thinking that we're seeing something rotating there in 3 dimensions rather than something happening on a flat screen, or a straightforward application of the scalar product. Okay, right, I want to dwell on games just for a little bit longer. I'd like to talk to you about some nice techniques in collision detection, and some of these were first used in some of the Asteroids clones that were around in the early 80s. Asteroids is a game invented by Atari, and actually I've got a flash version of it here I'd like to show you. Oh, maybe not. Let's try that again. Let's get rid of that. Okay, I'm hoping now that you can see Asteroids. You may need to sort of scroll the screen around a bit to see it properly. Okay, let me have a quick go on this, just so that you know what we're talking about. I'm sure it's updating really slowly for you, so it doesn't look very smooth, but you can see here that we're essentially firing dots at irregular polygons, and when the dots hit the irregular polygons, they smash up into smaller irregular polygons. That's Asteroids. And the thing I'd like to just show you very quickly here is a nice method for that collision detection. So how do you work out the moment that this bullet has actually touched one of your irregular polygons? Now, it's not that straightforward. There are lots of ways you can go about this. You can try to sort of equate. I mean, just thinking about what you actually know here, what you would tend to record for this polygon would be the coordinates of each of its corners. So you'd know an x and y coordinate here, 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 and here, and then you'd also know, of course, the x and y coordinate of the bullet that you're considering. So essentially the problem is you know these 2, 4, 6, 8, 10, 12, 14 numbers, and you've got to detect when this bullet has actually hit or touched the polygon. Not that easy. There are different things you could try. You could try calculating the equations of all these straight lines and doing some inequalities, some logic tests for that. But the most efficient methods use vectors, and I'd like to just show you one of those now. Really nice mathematical story as well. You can, of course, break down any irregular polygon into triangles by adding some more lines. So you can see that done for our asteroid here. And what that means, of course, is if you can work out when it hits a triangle, you can work out when it's hit any asteroid. So that reduces the problem to a triangular asteroid, and hopefully that will be easier. Of course, this is something that mathematicians do a lot. If there's a problem that's too difficult, they say, can we solve an easier version, and then use that to solve the original. So can we solve it for a triangle? Answer is yes. Let's call our triangle ABC, and let's think about a situation where the bullet is actually inside the triangle. The thing you have to think about is what would be the sum of that angle and that angle and that angle. Well, there it is. You can see that would be a complete turn, and it would give us in degrees 360. Whereas if we have a point on the exterior of our triangle, now P's popped up over here, the same three angles, APB and APC and APC, sum to something less than 360. So of course, by knowing the coordinates of A, B, C and P, we can calculate things like the vector PA and the vector PC and the vector PB. We can use the scalar product to calculate the three angles, and then we can sum them to see whether that gives us 360 or a number less than 360, and that will determine whether the point we were considering P is inside the triangle or outside the triangle. When I read about this, I kind of wondered whether that works. So I went away and tried to use Excel to see whether I could demonstrate that to myself. I'm hoping that you can see this now. I'm sharing Excel with you. Again, it may take a while to come through, and you may need to scroll it around a bit. So what we've got here then is these three angles are the three angles I was just talking about, and this is their sum rounded to the nearest whole number. I'm going to move the bullet out of the triangle, so you can see in this diagram that P is now on the exterior. If I move it towards the triangle, you can see that as it approaches the triangle, the angle sum increases, and then when it touches it, we actually get 360. While we're inside there, while the point is inside the triangle, it stays on 360, and when it pops out the other side, it goes back down below 360. If I move the point B in order to capture the point, you can see the instant I capture it is precisely when that angle sum becomes 360. So it's a really nice, efficient way to check whether a point is inside a polygon, and it's used extensively in collision detection in video games, and in 3 dimensions it works too. So that's a really sort of neat, fairly straightforward application, and especially if you build asteroids into the discussion, that makes it sort of come alive for young people too. Okay, the last thing I wanted to touch on here is social networks. Now, there's a lot to say about social networks. I'm electing to say just one thing. I'm not really sure if it exactly fits under social networks either, but it links in quite nicely with some of the other things that we've been talking about this evening. So, the thing that I'd like to talk about very, very briefly is this idea of recommendations in not only social networking sites, but also in e-commerce sites. So, for example, in iTunes, you'll see that you get things recommended to you. So somehow iTunes will look at your purchasing history, and it will look at all the products that it could possibly sell you, and it will attempt to match you to products somehow based on what it knows about your taste in music. How does it do that? There are lots of different ways that recommendation systems can work. I'm going to pick out just one of them, and it's an application of the scalar product. So of course we've just been looking at the scalar product. We know how this works. I remember when I first met this, I thought this was absolutely magical. Still do actually. Can't quite understand how this gives us an angle. So somehow by doing this operation on two vectors, the scalar product, it's the same as multiplying the length of the first one by the length of the second one, and then multiplying that by cosine of the angle between the two vectors. And this gives us a way to calculate the angle between the two vectors. Now, the reason that I really like this application is that we can calculate the scalar product in dimensions higher than 3. There's no reason that we can't multiply the first components together, and the second components, and third components, fourth components, fifth components, and then add and do the scalar product on n-dimensional vectors. Similarly, we can calculate a length of an n-dimensional vector using this generalization of Pythagoras. Just keep squaring and adding and then square rooting to get a sort of generalized length for an n-dimensional vector. And of course, most of the applications we see when we're at school, well, in fact, I think I'm confident to say all, are in either 2 dimensions or 3 dimensions. We don't really think about how vectors might be useful in more than 3 dimensions, and it's very difficult for us to really imagine how that might even be, because all the work we do in 2 and 3 dimensions relies on sort of geometry in a picture. I'm going to set this in the realm of internet dating, but I believe that iTunes works in a very similar way. Imagine that you sign up for this internet dating website and you have to fill in a questionnaire. You have to indicate somehow how much you like sport, how much you like music, how much you like theatre, and how much you like cinema. And there's a scale from -5 to +5 for all of them. So if you said you like sport +5, that meant you really like sport. If you said you like cinema -5, that would mean you really hated cinema. So, and 0 would be neutral. Okay, so here's our story. Joe and Jenny both sign up for this website, and they fill in the questionnaire. Joe says that he likes sport 5, he likes music 2, he likes theatre 1, and he likes cinema -3. And so he has this vector which represents his taste in these 4 areas. Of course, these 4 areas are the only things that would determine the success or failure of a relationship. Jenny, on the other hand, she likes sport 2, music 1, she's neutral about theatre, and she's -1 for cinema. So the question is, how compatible are Joe and Jenny? Well, what we're going to do is we're going to calculate the angle between these two vectors, ignoring the fact that we could never possibly draw them. We imagine that if the angle is low, it means that the two people, they kind of like the same things in the same ratio. That's how the two directions would end up being similar and the angle between them being low. If Jenny had the exact opposite taste to Joe, then her direction vector would point in the opposite direction to Joe's, and the angle between them would be pi, or 180. So let's have a look at how the calculation proceeds for Joe and Jenny. First of all, we're going to calculate the length of Joe's taste vector and the length of Jenny's taste vector, so squaring the components, adding, square rooting, similarly for Jenny. Then we do Joe dot Jenny, the scalar product, multiplying these and these and these and these, and then adding, that gives us 13. And so we calculate cosine of the angle between them by taking the dot product of their vectors, dividing by the product of their lengths. So cosine of theta for Joe and Jenny is 0.8498, which means that theta is low. Theta is a small angle, smallish angle. And so we've got some sort of indication of how compatible Joe and Jenny are. And sites like iTunes and Amazon, anything that will recommend things to you, operate systems similar to these. They don't all work using the scalar product, but certainly some of the ones on the big websites do. And of course, what happens is over time, as you use these websites, the website will collect more and more information about you, so it will be able to update your taste vector, say across different types of music genres according to the things that you've bought. The fact that you've bought something will enable it to update the vector describing that product. So it now knows more about the product because it knows somebody who liked that product. So over time these systems get more and more intelligent as more and more purchases are made, and presumably more and more accurate in terms of making recommendations. There's a really simple application there of a high-dimensional scalar product in recommendations. That's all I want to say about social networking, but there's loads of really interesting things there. I know that Peter, who gave the first talk, he gives a talk about social networks, which is really good, touching on lots of areas of graph theory. So that brings me to the end of my talk. The thing, of course, that I think I'd like everyone to take away from this is just an awareness that there's a lot of mathematics going on in some of the applications that we see on the internet and games and films. Especially if you get a chance to speak to young people about mathematics, remember some of these applications, because I've been using these for a number of years now, and I found that they work really well. They sort of pass what I call the half-past-4 test, which means, is this something that a student might be doing after school at 4:30, and is it sort of the mathematics of the everyday life of a teenager? And I think it is, and it seems to work really well. And also the mathematics isn't that difficult, so it's the kind of thing that students are learning when they're 14, 15, 16, 17, and you can show them exactly how that math is used, rather than having to say, well, a version of the maths you're learning now is used in this thing, which might be sort of something you might do if you study for long enough. You can actually show them quite direct links between some of the maths that they're learning and the maths in the technology that they might use. So I'd like to finish there. I hope you found that interesting, and I hope the technology wasn't too clunky with all the application sharing. If you've got any questions, then fire away now. But otherwise, thanks for attending, and I hope you enjoy the next one in the series, and good luck with all your maths, I guess. Okay, thanks very much everyone, and good evening. Stephen has posted a link for feedback. I believe you can paste that into your browser, and you can give us some feedback. With the show, yeah, it does actually. So if you take the kind of polygons that appear in asteroids, then you can always divide them into triangles like that, and it will work in 3 dimensions as well. So even if you're, sort of, we're talking about, say, a Tomb Raider game, and we're talking about a triangle which is part of Lara Croft, you can still use that to detect whether a point is passing through a triangle, making up a character in 3 dimensions. Yeah, well, it won't depend on the shape there. It will work for any angles. Yeah, it's really nice. It's really robust and really nice way to check that. I've got a three-dimensional version actually of that spreadsheet, which I'll be happy to send to you if you're interested. Yeah, I think so. Yeah, you would divide it into triangles, otherwise the mathematics would get much more complicated. If you look up on the internet point in a polygon,